Hi there. Okay, we are on our second to the last one of these. We're now going to be kind of talking about nonlinear clearance altogether. We've talked about nonlinear intrinsic clearance specifically because that's the one that caused the phenytoin, and we also talked about nonlinear binding, which also will affect clearance, won't it, for some drugs. And so we're going to talk about the nonlinear intrinsic clearance and the nonlinear binding again and how that would affect clearance, therefore the clearance being nonlinear. And then we're going to talk about one other source for nonlinearity, and that's renal clearance. Um, and renal clearance, tubular secretion has a rate limiting sites that can be overwhelmed. So we'll be talking about all three of those. Okay. Beep. All right. So with hepatic clearance, we have changes in intrinsic clearance that are subject to being nonlinear, and we see that alcohol, phenytoin, and salicylates are all drugs that we see nonlinearity in the therapeutic range due to nonlinear intrinsic clearance, causing a decrease in clearance as we increase concentration. And then we also have nonlinear plasma protein binding in the therapeutic range for salicylates. As your fraction unbound increase, as you overwhelm those binding sites, your fraction unbound will increase, therefore increasing clearance. So this results in a decrease in clearance with increasing concentration. This results in an increase in clearance in when you increase the concentration. So this nonlinear hepatic clearance only occurs with low extraction drugs because remember, low extraction drugs are dependent upon enzyme activity, which can be overwhelmed, and binding, which can be overwhelmed. But if we were looking at high extraction drugs, then for that clearance, is equal to liver blood flow. Liver blood flow cannot be overwhelmed with drug, so it is going to always be linear. I don't know why it does that. That's weird. So we'll keep moving here. So what you see in nonlinear clearance, as the concentration increases, as we said, when those enzymes get overwhelmed, as you increase the concentration, if they start to get overwhelmed and concentration becomes a factor, as concentration increases here, we're going to see a decrease in our intrinsic clearance if we have to consider concentration. But if our Km is much greater than this, we don't have to worry about it. That's linear. But if concentration has to be considered, then this all becomes important, doesn't it? And as our concentration increases, our intrinsic clearance will start to fall, which means our clearance will start to fall for those low extraction drugs. With nonlinear fraction unbound in plasma, remember again, is if the concentration needs to be included here, as our concentration increases, our concentration bound will decrease, which means our fraction unbound increases, doesn't it? And so if we have to consider concentration here, our fraction unbound will increase and our clearance will in turn increase because clearance is equal to enzyme activity and the fraction unbound. So if this is increasing, then our clearance is going to increase, isn't it? Now, this is the one we haven't really talked about. Remember, in renal clearance, we have three processes. We have filtration, reabsorption, and secretion. Filtration, we can have, again, binding that's nonlinear, which, remember, filtration clearance is equal to GFR glomerular filtration rate times fraction unbound. So if this is nonlinear, we're going to have nonlinear filtration clearance, aren't we? And active secretion is what happens next. Active secretion is where drug is being moved from the blood and going into the urine. And again, it follows Michaelis-Menten. So if concentration has to be in here, if the concentration is not much less than, then we're going to need to include it here. And as the concentration increases, our tubular secretion clearance will decrease, therefore decreasing the tubular secretion clearance and decreasing clearance overall. It's going to stay in the blood because it's overwhelmed these systems here. So not as much of it's going to be able to go back into the urine, so it's going to stay in the blood, so clearance will go down. You can have active reabsorption. Ascorbic acid is an example of that. So again, with active tubular secretion, it follows Michaelis-Menten, where TM are the number of binding sites available, and TM is the number of binding sites available, or the capacity of the system. Not binding sites, but secretion sites, secretion sites. Trying to write with a mouse, secretion sites. So this is the capacity of the system. This is the concentration where you're at half of those are full. So again, this is our affinity constant, and it's analogous to Km. But as long as our concentrations are much less than the KTS, then again, this falls out to be 0, and our intrinsic clearance stays constant as long as there's no change in the number of transport sites or in our Km. So as our concentration increases here, our intrinsic clearance tubular secretion will remain constant. However, if that's not true and we have to include the concentration, we're going to see our concentration, as our concentration increases, our intrinsic clearance will decrease, which will decrease renal tubular secretion clearance, which then in turn decreases total body clearance, which then, of course, increases half-life, etc., increases CSS average. You know what that all does. All right. Thank you. That's it.